So basic idea of Fenwick trees is that if you have an array, um, and again you should know this is just a quick recap, is if you have an array, right, and you're trying to get the sum of a range, like this range here, with a Fenwick tree or segment tree, you can get the sum in log n time. So that's just the data structure that we're going to be using for all these problems. Alright, let's start with the first one from CodeHorses. Oh yeah, and again, I'm not expecting as many people this time as usually because of the CodeHorses round. That's fine. Okay, so let's look at this problem. One day, Polycarp decided to rewatch his favorite episode of a well-known TV series, to Furama. He was pretty surprised when he only got the results, but he got the results only for season 7 episode 3 with a search query of season 3 episode 7. This got him confused. What if he decides to rewatch the entire series someday and won't be able to find the right episodes to watch? He now wants to count the total number of times he'll be forced to search for an episode using a different method. So, the TV show has N seasons, and the ith season has AI episodes, numbered 1 through AI. He wants to count the number of episodes with the number of pairs x, y, such that season X includes episode Y and season Y includes episode X. That's basically the thing that he's trying to count. The number of these. Okay, so let's look at that. Basically what that's saying is like, do you have the pairs 3, 5 and 5, 3? Right? Then season 3 contains episode 5 and season 5 will also contain episode 3. So then you'd add 1 to your answer. You want to count the number of pairs like this. So, okay, the first thing to notice is that yes, AI can be up to 10 to the power of 9 as it says here, but that's really sort of a trick because since the number of seasons can only be up to 2 times 10 to the power of 5, it doesn't matter how big AI is because any AI that's greater than n will never be part of the answer, right? Like let's just say you have uh, x comma 10 to the power 8 here. It's impossible to have 10 to the power 8 comma anything. This you simply cannot have, because 10 to the power 8 is not a possible season. So you can reduce AI to the minimum of what it currently is, and n. Alright, so the next thing we need to realize is, okay, so the total number, since each season we only care about the first n episodes, right? And the maximum our answer can be is n times n plus 1 over 2. And this is because for, actually I think it might be a little higher, but it's basically it's somewhere around order of n squared. So we can use a long and this one overflow. And this can also be implied for the fact that we don't have to take mod of anything. Alright, so okay. So now let's count things like one at a time, right? So let's look at this sample input here. Okay, so first of all, we can change it from 8, 12, 7. We can change it to 3, 3, 3 because we take the minimum of what it currently is in n. Okay, so now from 3, 3, 3, alright, so this means, so instead of counting the number of pairs, we cannot loop through all pairs of seasons to count the number, to see if there's an overlap, right? So what we have to do is we have to count for each season. We want to find all of the overlaps that involve that season in basically log n. So we do this for each season, we loop through all the seasons, and we count the number of overlaps. So let's just say that we're looking here at season 2. Okay, so actually this is a pretty bad example. Let's just say our sample was like, let's look at the third sample where we have 3, 2, 1. Okay, let's say we're looking at season 2 here. This, the value of AI is 2. What this means is that the only possible combinations we have is there could be x comma 1 and x comma 2 for uh, for x as being a previous value. So actually we don't even have to write x, we can just put in the, oops, okay, 2 comma 1 and 2 comma 2, 1 comma 1, actually 2 comma 2 is not even a thing. This is probably a bad example also, but this is just something to look at, right? Actually, let's just, sorry about this. Okay, let's look at this third one here. It's a 1. So let's just use a different sample to make this clearer. Sorry about this one more time. Okay, last time I promise. So we have 2 here, right? This means, and this is at season 3. This means the 2 collisions it could possibly be a part of are 3 comma 1 and 3 comma 2. These are the 2 possibilities. These are both possible things. So for these to work, we have to ask the question, is it possible, does 1 comma 3 exist? And does 2 comma 3 exist? This means does season 1 have an episode 3 and does season 2 have an episode 3? Okay, so we can see if season 1 and if season 2 have an, so we cannot ask this for each and every individual one, right? But we need to count, basically what we need to do is we need to count the number of seasons that have an episode 3, such that the season number is less than or equal to the current season number. So this is 2, right? And this is 1, 2, 3. So for everything 2 or less, we need to count the number of those seasons that are greater than or equal to 3. Okay, that's basically the algorithm. Any questions? And again, feel free to ask questions for as long, and then I'll just check back in a minute because the lag, and I don't want to just sit here quietly for a minute and make everyone bored. So I'm just going to keep moving on. But yeah, feel free to ask questions. Okay, so now we need a data structure that for a particular index or less will count the number of, so this data structure will say for every index less than or equal to 2, how many A of I are greater than or equal to 3? Because 3 is the current index. Okay, so obviously this lecture is on Fenwick trees, segment trees. So we can use either of those. I'm going to say Fenwick tree, but you can use a segment tree just as easily. Okay, so we need to count the numbers in a particular range that are less than or equal to the current value. So I'm going to just open my code, because this is the easiest problem, so I don't want to rewrite the code, and I'll just explain the code. I'm sorry if there's a bunch of defines, and those are just segment tree stuff. You can use a Fenwick tree. So I'm just going to actually, no, we shouldn't use this. Okay, so let's just do it from here directly. What we can do is we can look at the inputs and values of greatest to smallest. We look at 5, then we look at 4, then we look at 3, then we look at 2, then we look at 1. Here we will look at 12, and then we look at 8, and then we look at 7. So we go from biggest to smallest. Okay, so we go from biggest to smallest, right? So, and the idea behind that is, that, so we try to find everything that is greater or equal to 3. The count of the values less than u that are greater than or equal to 3, right? So this means that, alright, so let me just explain this a little more in detail. So we have our tree, and we have the value that we put in the Fenwick tree is the index. Okay, so let's just say this is 1, this is 2, this is 3, because then it's 3, so the rest don't really matter. Dot, dot, dot. Okay, so we look at the first value, 3. It's the biggest. And that's at index 1, so we put a 1 here. Then we look at index 3, because it's the biggest, right? So then what we do is we query the number of values, we query the sum of the previous, and of course everything starts out at 0. So the sum of the previous is 1. And what this means is, it means that 3, this 3 here will have, oh, I'm sorry, sorry about that. Okay, it means that this 3 here will have one collision with one of these pairs, such like 1, 3, 3, 1. It'll have exactly one pair that works, because the sum is 1. And then the next thing we do is we look at our next biggest value, and it doesn't matter which value we look at. We look at the black values on top, like the AI, before we look at the indexes. It doesn't really matter which order. So we get this 2, and this is at index here, so we update that to 1. Then we look at this 2, this is at index 3, so we update that to 1. And we look at this 2 here, and we query the sum of everything less than it. That's 1, so we add that again to our answer, and our total sum is 2, which is the output. Okay. Are there any questions, and do I need to code this? I don't think the video is the video still? I guess try refreshing. Okay, I'll take no answer. Oh yeah, that's my bad. Okay, that was my mistake. Okay, so I'll take no answer as I don't need to code this problem. And yeah, okay, cool. I'll just move on to the next problem. So just remember, when you're coding it, first look at all the black values, and when you look at, and then look at the indexes on the bottom, right? So you first look at the AI, so you loop through from I equals n down to 0, then you try to find all the AI that equals, or all the AJ that equals to the I, which would be 3 at first, and then you find the index and you do it. There are no AJ, you just straight go to the index. Okay, no code school. Alright. Next problem. Balanced photo. Farmer John is arranging his N cows to take a photo. The height of the ith cow is HI, and all the heights are distinct. As with any photograph of cows, Farmer John wants this one to come out looking as nicely as possible. He decides that cow I looks unbalanced if Li and Ri differ by a factor of more than 2, where Li and Ri are the number of cows taller than I on the left and right respectively. That is, I is unbalanced if the larger of Li and Ri is strictly more than twice the smaller of these two numbers. Strictly more. Okay, cool. Help Farmer John compute the total number of unbalanced cows. Okay, so look at the second one, or let's look at the sample input here. We have 34, 6, 23, 0, 5, 99, 2. Okay, so now there's a way to solve this problem without using Fenwick trees, but we are going to use Fenwick trees. So, okay, so just to clarify, Li and Ri are the number of cows taller than I on the left and right. Okay, so let me just scoot these over, or so we can compute Li and Ri. 0, 1, 1, 3, 3, 0, 1, 2, 3, 4. And Ri would be 1, 1, 2, 1, 3, 1, 0. Okay, so 34 is an answer because 1 is greater than twice of 0. This is equal, that has to be strictly greater. And this is 5 is an answer because 3 is strictly greater than twice of 1. And 2 is an answer because 4 is strictly greater than twice of 0. Okay, so alright, if there's time, I will go over the other way. Basically involves using sets. Okay. Then I'll discuss the other method also. It basically just involves using sets. And yeah. Or not sets, sorry. A segment tree with vectors. I'll discuss this method too. It's also a data structure method. But yeah, it's okay. Basically, the other method is more complicated than Fenwick trees if you don't know it. Or it involves a more complicated data structure, but the algorithm is very simple. Like when I look at this problem, the first method I think of is this other method that I guess I'll also go over. And it's just oh, this will be shared later. If I didn't express it earlier, sorry. Yeah, so the other method, it's just the first thing I think of, and it's fairly easy to code, ish, if you know how to code a segment tree. But like this other method just involves this. Sorry, the first method just involves this Fenwick tree, but you have to think of the algorithm. So okay, I'll go over the other method too. Alright, cool. So h can be at most 10 to the power 9, right? So basically, if we can compute this L array and the R array, I guess if we compute the L array, the R array can be computed symmetrically, then we can solve this problem. Okay, so alright, so let's just start off with, okay, so the first thing to notice is that these values can be up to 10 to the power 9, right? But we don't actually need them to be this big because, so they said all the heights are distinct, right? But there's only a total of 10 to the power of, n is up to 10 to the power of 5. This means that if h is up to 10 to the power 9, there's a lot of values that are skipped. So the first thing we can do with these heights is we can coordinate compress them. For example, we'll coordinate compress so that they're 1 to n. So this 0 will become 1, and 2 becomes 2, 5 becomes 3, 6 becomes 4, 23 becomes 5, 34 becomes 6, and 99 becomes 7. Okay, so now that we have this coordinate compressed version, now to find this L array here, and symmetrically for the R array, you need to be able to count the, so the L array is the same for this compressed version we have here, right? So now we don't even need this other array here. We can just remove it. So now all we need is with the new array, so L array basically means we need to count the number of bigger values than you on the left. And we can do this with a Fenwick tree similar to how we would count inversions. Alright, so let's make an array of size n. 1, 2, 3, 4, 5, 6, 7. Okay, so originally everything starts off as 0. Okay, so we loop through, we look at 6, right? So we're trying to count the number of values bigger than 6 to the left of it. So we're looping left to right. So at 6, we're counting the number of values that we have already passed, which are bigger. So we query this, we get 0. So that means this value here is 0. Okay. Then since we're at 6, we update 6 to 1. Because we now have passed 6. And we'll look at the next value, 4. So to find 4, what we do is we query everything bigger than 4. We get a sum of 1. So this value here is 1. Then we update the 4 to be 1. Alright, cool. Next we're looking at 5. Oh, and that comma just went. Cool, so next we're looking at 5. So we query everything bigger than 5, and we get the sum of 1. So that value there is 1. Then we update the 5. Then we update 5 to be 1, because we just passed 5. And so on and so forth. We do this, and that'll get us the rest of our values here. And then we just loop backwards and do the exact same thing to get these R values here. Okay, just to be clear, on how to, actually, do I need to go over how to get a range of a Fenwick tree? Also, do I need to code the method I just went over right now? If you think I need to, okay, let me know if I need to code it. I'll take no answer as no need to code it. You can just keep letting me know for a couple minutes. Or because of the lag, so I'll just leave that open for a couple minutes. Okay, the other method. You can create a, I'm just going to write down the original array here. Okay, you can create a segment tree where every value in that tree is a vector. So, it's a vector that contains in sorted, which a vector which contains all the elements in that range sorted. Okay, no coding, that's great. Alright, so for example, I'll put the tree in this purplish color. The big root node, I'm assuming you know segment trees for this. If not, don't worry too much about it. This is just a bonus solution, I guess. Okay, I put all these values in sorted order. Right? And then your left child is the left 3 values in sorted order. and your right child is the right 4 values in sorted order. That should not be 6. This is the leftmost value. Oh, sorry, this thing's cut off. Okay. Okay, so this is basically what that segment should look like. Now, originally, when I first started this, I thought the memory would be O of n squared, but it's actually O of n log n because it's a seg tree, which means you have log n different steps, and each step has a total of n, right? So this one has a total of n memory, total of n here, total of n here, O of n here. So that memory is good. Oops. Okay, so now if you want to solve this problem, to find the L array here, and symmetrically for the R array, for 34, we just do a query, or let's just say for this number 23 here, right? We just do a query for everything left of 23 that for everything left in 23, and we just count the total number of values bigger than it. So we would do a binary. Actually, that's a bad example. Let's just look at 5 here. Okay, so we take everything with a previous index. Those are these two segments here. We binary search and we count the number of ones that are bigger than it, or bigger than it. So nothing here, nothing with the 0 here. But for here, all 3 of these are bigger. So the answer for 5 would be 3, as it is. Oops, sure. Okay. Let me know if you have any questions about these, or about this algorithm. And I'll just leave the questions open for a couple of minutes. And let me know if you want me to code this algorithm. Because this is a tougher one to code, but it's easier to think of during a contest. It's a lot easier to think of. So let me know if you need me to code this right here. I'll start moving on to the next one, but actually I'll just, no, that's fine. I'll start moving on to the next one. Let me know if you want to code this, and I'll just code it then. Okay, I'm just gonna, I'll leave this open so I can see the lag. Okay. The layout of Farmer John's farm is quite peculiar. The large circular road running around the perimeter of the main field on which his cows graze during the day. Every morning, the cows cross the road on their way towards the field, and every evening they cross again as they leave their field and return to the barn. As we know, cows are creatures of habit, and they cross each road the same way every day. Each crosses into the field at a different point from when she crosses out of the field, and all these crossing points are distinct from each other. Farmer John owns n cows, conveniently identified 1 through n, so there are precisely 2 n crossing points. It seems like the lag has gone down a bit. It's 25 or 35 seconds now, so that's pretty good. Farmer John records these crossing points concisely by scanning around the curl clockwise, writing the ID for each cow the crossing points, ultimately forming a sequence with 2 n numbers, which each one appears exactly twice. He does not know which ones are entry and exit. Looking at the map of the crossing points, he is curious how many times various cows might cross each other during the day. He calls a pair of cows crossing if they cross, basically. Okay, you have 50,000 lines, or you double that 100,000 lines because next to a line, and you want to find the number of crossing pairs. I don't know what that was, but cool. Alright, I guess I'll code 4 and 3 in this one if I have to. Okay, so let's draw this out. Sample. We have 3. That's a bad 3. 3, 2, 4, 4, 1, 3, 2, 1. Okay, so in terms of the pairs, they look something like this. Okay, cool. So our 3 crossing points are here, here, and here. We just need to be able to code this. And just looking. Okay, looks like there's no questions about the previous method, I guess. Alright, cool. So, and of course 4 doesn't cross with anything because they're just next to each other. Cool. So, we can do this. So first of all, we're not given this in a circle, we're given it in an array form, but we can sort of make it into a circle pretty straightforward, pretty easily. So let's just start with, okay, so we'll loop through the points obviously, right? And okay, so let's make our friendly tree down here. And we'll have it up to n. Okay, so for every cow, we need to know, like within its path, how many cows cross it. So it doesn't really matter if you count a path like this or like this, because you count a path one way, and basically if there's a cross, it'll occur no matter which way you count the path. Because notice how 2 and 1 occur once in this path, and if you go this way, 1 and 2 also occur exactly one time. Okay, so what we can do is, we start our loop, right? And since the first thing we're given our input is 3 there, we start at 3. Okay, so we're just going to loop forward because that's just the easiest thing to do. So we're going in this direction. Okay, so the next thing we look at is 2, right? And we want to figure out, oh, first, yeah, let's just look at if we were to do a brute force solution, because brute force is the first thing you should think about. It's how do we know if 2 intersect, right? So let's just say that the first cow is at AB, and the second cow is at CD. They intersect if A is less than C is less than B is less than D. Oh, of course, C is less than D and A is less than B. We'll put these in short order, of course. Or C is less than A is less than D is less than B. Right, one of these two must be true in order for this to work. Okay, so now for 3, right? 3 starts at 1, and actually I'll use a different color that's not purple to make it a little clearer. 3 starts at 1. 3 starts at 1 and ends in 6. So let's say we only consider this option here for cow A, and this option here will automatically be considered for cow B. Or, yeah, sorry, for cow that starts with C. So the cow that starts with C will consider this option, and the cow that starts with A will just consider the first option. So right now we're only looking at this first option here. Okay, so now we're trying to count the number of cows, C and D, such that C is between A and B, and D is greater than B. Or D is less than, we'll count greater than B, including less than A, because of course it's a circle. Okay, so we don't even need to consider D, because we will just, so D can be in 2 places, right? It can either be greater than b or less than a because it's a circle. So we'll just count the number of times that there's a c in the middle and b is not between a and b. So we'll just count those. Okay. So let's just go through the cows and we'll mark the first one as starting and the second one as ending. The first time we see it as starting, second time we see it as ending. So this is a start, this is a start, this is a start, this is an end, this is a start, this is an end, this is an end, this is an end. Okay, now for every, so let me just make this array here slightly bigger. Now for every starting location, we will put the ending location. So it starts for this first cow here, right? The starting location is 1 and the corresponding ending location here is 6. Okay, for this pair here, the starting location is 2 and the ending location is 7. For this next pair here, the starting location is 3 and the ending location is 4. And for the last pair, where's the last pair? I think it's this one. The starting location is 5 and the ending location is 8. Okay. So I'm first going to talk about the segment tree solution, and then we can convert that into the Fenwick tree solution. That's a bad 3. What do you mean by bad 3? Oh yeah, that was a bad 3. I mean, I fixed it, so it's all good now. Okay, so now we're focusing on this equation, or this focusing on this formula right here, right? So let's consider the cows in order of index. The first cow is cow 1. It starts at 5 and it ends at 8. So we want to know the number of cows in between 5 and 8 such that, that start in between 5 and 8 such that their ending location is not in the range of 5 to 8. Oh yeah, and this formula could also include loop arounds for a is less than c is less than b. But this basically means just a circle. Okay, so what we can do is we can query, if you're using a segment tree with vectors, as I said for the previous problem, I'll show this into a Fenwick tree next. We can query this range here, and we can count how many of these values are greater than 8, or I suppose 1, 2, 3. Like it's basically not in the range of 6 and 7. And the answer is 0. So we're not going to count any of the 0 stuff here. And that's cool. So then we go on to the next one. We look at 2. And this is the range 2 to 7. So we count how many values here are not in the range of 2 to 7. And that's 1 value. That's the 8 there. So the answer is now 1. We had 1 to our answer. Okay, and then we look at our next one, 3. And this is from the range 1 to 6. So we look at this range, we see how many values are not in the range 2 to 5, and that's 2. So we add 2 more to answer, and our answer is 3 at this point. And then we look at the range of 4, 3 to 4. Oops. And of course, there's nothing in between 3 and 4, so we just add 0. So our answer is 3. And this is if you're using a segment tree with a vector at each index that I described for the previous problem. Okay, so now how do we change this to a Fenwick tree? Because the Fenwick tree is also obviously a lot easier to code, and it's better for beginners. So, okay, what we can do is, we can go, actually, do I need to go over the Fenwick tree solution, or are you guys good with this solution? Because I think we're kind of running out of time if I'm going to code these. I guess I'll just start discussing it, and then I'll just wait until the lag expires and you hear my question, I suppose. Okay, so now let's consider this 3, right? In the range of 1 to 6, we need to count the values here that don't end here, right? So we need to count the starting values that start here, but that don't end in this location. So since it's a Fenwick tree, we're obviously going to use plus and minus ones. So instead of putting these values, actually I'll keep that thing. Okay, so what we can do is we can, for the segment tree, for each thing that's a start index, right? We'll put a +1, and for each thing that's a end index, we'll put a -1. But we only care about maybe the segment tree one. It's a tricky implementation of Fenwick tree, so I suppose coding it would not be a bad thing. Also, the Fenwick tree solution you can find online. Okay, cool. I'll just code the segment tree one. Actually, the find int long, because I think the values can be pretty big. Can I double the size because you actually have twice as many values as n? Okay, segment trees are supposed to be size 4 times n plus 1. And then we need to mark everything as either a start or end. Okay, so let's just store the 2 locations of every value. Actually, where does it? Okay, we're gonna. This means we haven't seen this value before. Otherwise, we have seen this value before. Set B. Okay, so now for every value, we know if it's a starting or if it's an ending value, and for every possible number we can see for cow, we know the start and the end value of it. Now we need to, I'm just going to write the, this is the build function. Okay, so we'll put the values that's supposed to be on the tree in this on array. We only care about, we're looking at all the possible cows that could be passing. And we store the end value for each of the possible start values. Okay, all the other ons should, so for, we need to initialize this on array or something, to something. I'll say -1 for now. Actually, we want to count the values that are not in the range, so I'll just say I. Okay, then we'll build the tree. Oh yeah, our tree has to be a vector. Not a... Actually, okay, we'll put this as -1 and we just won't push it into the tree. If it's not, if it's -1. So it's not equal to -1. Then tree index dot push back. On. Okay, and then we'll just copy the values over from our child trees. We could use word sort to just combine them, but there's no need to do that speed up. Okay, so now we got a tree built. Now, for every cow, we need to have our out variable, which is what the answer is. Now, for every cow, we need to query the, of course, this is just to get the range. We need to query the number of cows in the range. So I guess we'll just query the, okay, so there's guaranteed to be a positive range, and that's the one we're trying that starts small and ends big. So we're guaranteed that this is a positive, that we can do infinite dot, that we can do this, and that we're guaranteed that this will not be looping through a circle, because we're guaranteed that this is looping through this version here and not this version here, based on the way we picked our inputs. And if yours isn't, you can just, I guess, sort them, or sort these two. Okay, just make sure there's no questions. Cool. Okay, so we want to count the number of numbers in this range that are not in this range. And then of course at the end we just print out. Okay, first thing we do in this, we check if we are not in the range. So again, OL and OR is the range that we're trying to query, and L and R is the range that we're currently on. Then we check if L and R is completely inside the range we want. Okay, and then otherwise, and this will just return something. Otherwise, we return the queries of our two children. Okay, now here we need to do a binary search, two binary searches actually, to find to find the small and the biggest value that works. So find the smallest value that works first. Or no values work, right? So the first thing we do is, so let's just see. Oh yeah, first of all, if tree index dot empty, then this means no values work and we just return 0. Okay, then we find the smallest value that works. So we check if the last, and they're in sorted order, we always sort them. So we check if the last value is sorry, find the, actually, what do we mean by the smallest value that works? Okay, so find the smallest value that is in the range. Okay, so if the last value is less than the range, then all the values are in the range. Values are not in the range, sorry. So here we return, so all the values are not in the range, we can just return all of them. Okay, and then here we do a binary search. Okay, so look at the minimum value is less than the left value. Then we need to say our mid equals, oh sorry, our A equals, because our mid is too small. Else B equals mid. Okay, so now A and mid are equal, A and B are equal, so our start is A. Or B, doesn't really matter, they're the same. Now we need to find the biggest value in the range. So the first thing we do is we do an if statement to see if all the values are too big, that means no values are again in the range. But once it be, oh right. we return 0. Oh, sorry. We're trying to return the values that are in the range. That are not in the range. No values are in the range. Okay. Then we do the binary search again. Okay, so this time, if it's less than the right, then we like it. Otherwise, we need to reduce it by 1. Just add 1 there because we're subtracting 1 here, so we add 1 there. Okay, and then we return a minus start. Okay, let's run this. Supposed to go on postman for sure. Oh, right. A and B are just. I'll just define A first and B second. $94. Oh, input's the wrong one. It should be lock. Okay, 3. Okay, let's add in the input. File input. What? It worked on. Got it here. I don't know why it's not. Okay, I mean, there's obviously some undefined behavior that's acting differently in both. I could debug it, but I don't think that would be the best use of the time right now to do. So I'm just gonna move on to the next problem if that's okay. Just so we have enough time to go over all the problems. Okay, Farmer John is attempting to sort his N cows before they head out to pastures for breakfast. Currently, the cows are standing in an order, and he's in front of the first cow. He wants to reorder the cows so that they're in order. Today's cows are sleepy, so at any point the only cow paying attention to his instructions is the cow directly facing Farmer John. So in one one's time step, he can instruct his cow to move k places down the line, for any k between 1 and n inclusive. The k cow swing passes moves forward, making room for the cow to insert herself in the line after them. For example, if you have this, and cow 4 moves down 2 places, 4 ends up. Okay, so using eager to sort the cows, help him find a sequence of instructions so that he sorts the cows in the minimum steps. There are multiple instruction sequences. Your program may output any of them. Okay, cool. So the first thing we need to do for this problem is we need to figure out the minimum number of instructions you need to give. Okay, so there's no reason that Farmer John should give more than n instructions. If there are n cows, it should be possible for each of them to move exactly 1 time and insert themselves in the right order. At the very least, to make this possible, right? Let's just say that the order of the cows is 3, 2, 4, 1. Okay, So at the very least, what you could do is you can move every cow exactly once and start it in a new sequence. So currently, I'll mark this in red, nothing is fixed at the end. So then we move cow 3 all the way down to the end. So we get the order of 2, 4, 1, 3, where cow 3 is fixed. Then we want to add cow 2, we want to add it to the fixed sequence, so we add it right there. And this gives us the sequence of 4, 1, 2, 3, where 1 and 2 or 2 and 3 are fixed. Then we add 4 to the fixed sequence, we add it at the end, and so on and so forth. And you can even add cows in the middle of the sequence if necessary. There was like a 2.5. So at the very most, we will have to add n cows to the sequence. We'll have to move exactly n cows. Now, the thing to realize, oh yeah, I'm gonna check if there's any questions. Cool. Okay, so at the very best, or at the very worst, sorry, we'll have to move all the cows to the end to get them in a sequence. Now, the thing to realize is in this sample input, right? In the sample here, oops, 1 is already in order. We don't have to move 1 another time. So we can just keep 1. In fact, we have to move all the cows except for some range at the end that's in an increasing order sequence. So we just need to find the length of the sequence at the end that is in increasing order. In this case, it's 1. Right now in the sample input, oh yeah, and then we do, the answer is n minus the range at the end. Okay, so let's look at the sample input. 1, 2, 4, 3. The largest range at the end that is an increasing sequence, continuous range is 3. Because if you extend it to 4, then it's no longer in order. So the range at the end is 3, is 1 value. Range is equals to 1, so n minus 1 equals 3, and that is the minimum number of times required to sort the cows. Okay, so now what we need to do is we need to figure out, oh yeah, and you can prove that this is right, because you have to move, okay, so let's just say you have to move a particular range of, so basically you have this value 4 that's bigger than 3. That means 4 somehow has to go to the right of 3. That means 4 has to be moved. Oops, get back to this. Okay, 4 is bigger than 3, so 4 somehow has to go to the right of 3. So 4 has to be moved, which means everything before 4 also has to be moved. The maximum number of cows that don't have to be moved is the longest increasing sequence at the end, and that is actually, there's no reason to move any of them, because you can move everything else and just insert it into that. Okay, so now we just need to find the sequence, right? How do we find a sequence of moves? So we know that our fixed range at the end, we know what our fixed range at the end is. So to figure out how many cows the say 1 has to pass, well, it has to pass all the cows that are not in the fixed range at the end. I'll use a different color for that. Plus the number of cows in the fixed range that are less than it, which in this case is 0. So it's just passing a total of 2. But now let's just say the fixed range is 1, 2, 5, 6. You have the value 3, 4 here, right? So you have your fixed range of cows at the end here. And you want to figure out where to insert 3. So 3 has to pass all the values that are not in the fixed range, which is 1. And this you can solve using math. and then it has to pass a number of values in the fixed range that are less than it. Okay, so we can calculate the number of values in the fixed range that are less than the current value using a segment tree. So you know that the values are from 1 to n, so we don't even have to coordinate compress, right? Okay, so for every time so let's just go this way, right? Let's add all these values to the segment tree. So we have 6, we add it, 5, 1, 2. We add a 1, and everything else is 0. Okay, so we can use simple math to figure out the number of values that are not in the range. It's just n minus the number of values in the range minus 1, because you don't want to count yourself. Okay, now we need to figure out the number of values in the range that are less than you. So if your number is 3, you just sum up everything in the Fenwick tree that is less than the current value. I don't know why this is 3. Cool, so it's 2. So there's 2 values less, right? So then we have to move a total of 1 for this plus 2 for the segment tree. So 3 moves total of 3. Then we know that we have the value. We actually don't even need to store it. We could add a 3 here, but this would take too long. So we're not going to do that. We are just going to add a 1 here in the Fenwick tree. So now when we look at the number 4, because we're looping left to right, then we take the sum will be 3. And I'll have to move 3 values to the right. Okay. I need a code. If not, you can just end early, I suppose. Otherwise, I'll code it. Oops. I guess I could work on debugging this problem. If not, do we have 15 minutes left? Okay, so I'll code it, I guess. Cool. So if you're not interested in seeing the code, I mean, you can just tune off. You can rewatch other parts of this video, or other videos, I guess, or you can look at the code first. I mean, basically, if you're not interested in seeing this code, that's perfectly fine. You can just tune off, because remember, this is the last thing we're doing, so you're good. I'm just gonna keep coding it though. I think I can code it in 15 minutes. Okay, so we need to find the longest. We need to find the finished range at the end. We'll start the range at 1. It has to be at least of size 1. And okay, and then we'll say current I equals n minus 2 attributed name equals to 0 minus minus. if input of I is less than input of I plus 1, then we add the current value to the range, else we break out of the loop because the range is open. I'm just going to print the range here, just to make sure this works. Okay, cool, 1 is right. Okay, so the first line of output actually is in minus. Okay, so now, actually let's just call this out1. And we'll just print all the output. Okay, for all these values that we need to change, oh yeah, we also need our Fenwick tree, and I just have the code here, so I guess I'll just keep, it's just a quick Fenwick tree code. Change one to max in. Yeah, actually let's just print these as we're going. So print out one here. And then here we'll write, okay, so we need to print the number of values that it's skipping is n minus whatever is in the range, minus 1, because we're not skipping ourselves, plus the number of values in the range that are smaller than us. Okay, so we'll take the prefix if you want to query the number of values in the range smaller than our current one, which is input I. Also, when we put the value in the range, we have to update. So we update input n minus 1, and then here we update input I to 1. Okay, and then when we put this in the range, the size of the range increases. Two, 1, that's not right. Oh yeah, because we're putting this in the range, we have to update input I to 1. 2, 2, 3. Okay, that's right. These are, oh, I guess they care about this extra space at the end. Oops. Okay, this program works.